All right, so we left off, we're trying to build a perspective, so some frame of reference to talk about radiation. We learned there's different sources of radiation in the world around us, including natural and man-made, and those two accounted for about 5 to 6-ish milligray worth of exposure per year. What we need to do now is talk about the different types of radiation. So, in this section is titled radioactivity. But I want to ask you guys, when you hear radiation, what do you think? What's the one word that pops up? And this is better. I think my newer students are going to be more helpful with this. What do you hear when you think radiation? Ooh, waves. I like waves. Okay, waves are good. That's not usually what most people think, but I like that. That's right. Anything else? Expansion. Okay, good. Microwaves. Does anybody think harmful?
Oh, yeah.
Yeah? Okay, good. That's the most common answer I get when I go, what is radiation, right? What is the one word thing you think of when you think of radiation? Most people go harmful, right? Dangerous, right? I got a bunch of good answers. Those are some good responses. You guys are really thinking. Okay, good. So radioactivity, radiation, let's learn about it. Let's learn about the different types of radiation and where radioactivity fits in, okay? So we're going to put radiation into basically 3 categories, okay? We've got waves traveling through a medium, including waves traveling through water, or sound waves traveling through air, or like earthquake waves traveling through the earth, right, when there's an earthquake, yeah? Those are waves traveling through a medium, right? So you guys can hear me talking, right? What's the medium allowing me to make sound go from my mouth to your ears? It's the air in the room, right? My mouth is the mechanism. It's the thing that's vibrating the air in the room, but it's the air in the room that's vibrating. The sound waves are traveling through the air in the room, okay? You guys ever heard the phrase, in outer space, no one can hear you scream? Yeah, it's because in outer space, there's no air, right? There's a vacuum, in other words, in outer space, okay? If you scream in outer space, there's no sound created, right? Now, don't go outside of your spaceship and spacesuit and scream in outer space because bad things will happen to you otherwise, but you won't be able to make any sound, okay? Sound comes from air, compression waves in the air, okay? Similarly, water waves, the water is the medium for those waves. The medium is the thing allowing the radiation to propagate, allowing the radiation to move, right? Water or air in these 2 cases. That's category 1. Now, of course, these can be harmful, right? A big enough sound wave can hurt your ears, right? If you've ever been to a concert, right, you know that when you leave the concert, somebody tries to talk to you and you're like, what? Because you can't hear anything, right? Your ears have just been damaged that whole time, right? You might have lasting damage to your hearing ability after that point, right? A big enough water wave is also harmful, right? A tsunami wave, right? It's harmful. So radiation can be harmful in certain forms, and it can be non-harmful in other forms, right? Particulate radiation is going to be an exception to this rule, okay? Particulate radiation will be harmful all the time, okay? Particulate radiation includes variations of protons, neutrons, and electrons emitted at high speed from radioactive atoms. So they use the word proton, neutron, electron, and the word atom, right? I don't know that everyone knows what those words are, right? So let's go down level of structure, okay? Let's talk about you, right? Your body is made of systems. You have 11 body systems, right? Your cardiovascular system, your pulmonary system, your integumentary system, your skin, right? Okay. All those systems are made of organs, okay? Organs are made of tissues. Like your heart is an organ. Your heart's made of several different types of tissues, right? Endocardium, myocardium, epicardium. So you have tissues. Tissues are made of cells, individual little living things, right? Cells are made of molecules. Molecules are built out of atoms, okay? An example of the most common molecule in your body, what are you mostly made of? Water, right? H2O. Two hydrogen atoms, 1 oxygen atom makes the molecule for water, H2O, okay? H2O, water, is made of, as I just said, 2 atoms of hydrogen, 1 atom of oxygen. The atoms are the smallest component. Okay, they're the smallest component of a chemical, in other words, right? We call these individual components elements. Okay, you guys were all just handed a periodic table of the elements. Now, those atoms that are the smallest component of an element, they're further subdivided into three separate things. Atoms themselves are made of protons, neutrons, and electrons. These are the particles that make up atoms. Radioactivity is when you have an atom that's unstable and shoots off or emits at high speed little pieces of itself. Okay? Those little pieces can be variations, different combinations of protons, neutrons, and electrons, the pieces of the atom breaking apart. Okay? Atoms are the smallest thing, right? The smallest component of a thing, but they're made of their own pieces, their own three individual pieces. Atoms are very small. Okay? Atoms are about 1/10 billionth of a meter. You guys know what a meter is, right? How big's a meter, roughly? You don't know what a meter is? A meter is about 3 feet long. Okay. Where's my meter stick? Where's my meter stick? Okay. That's a meter, right? 3 feet 3 inches. Okay. Take this meter stick and chop it up into 10 billion pieces, right? Every one of those pieces will be 1 atom wide. Okay. It's 1/10 billionth of a meter, or 10 to the negative 10 meters if you like exponents. That's how big atoms are. They're incredibly tiny, right? Atoms made of particles, electrons, protons, neutrons. When these atoms are unstable, they break apart and shoot off little pieces of themselves. That's particulate radiation. We'll discuss that. That's what we're going to call radioactivity. Okay? The third category for radiation is electromagnetic radiation. Electromagnetic radiation is going to sound complicated, and then you're going to go, oh yeah, I know what that is. Double waves propagated in the electric and magnetic fields. That's the way to make it sound complicated. But it's light. Okay, and you know all about light because you've dealt with it your whole life, right? As long as you are a seeing person, a sighted person, you've dealt with light your whole life. Even if you couldn't see, you know what certain types of light feel like because you felt heat before, okay? Heat is infrared light. It's light that you cannot see, but you can feel, okay? So electromagnetic radiation includes visible light. The light coming from these light bulbs is electromagnetic radiation. This is why when I say X-rays are kind of like light, this is what I mean, okay? They're the same kind of thing, okay? The reason why you can detect the visible light in the room and not X-rays is because you don't have receptors in your eyes for X-rays. They're a different kind of light. You have receptors in your eyes for visible light, okay? The reason why your eye receptors are only sensitive to visible light is because you evolved on Earth, and Earth gets majority of its radiation in the visible spectrum from our sun, okay? Most of our light comes from the sun, and most of what the sun puts out is in this spectrum. It's in the visible light spectrum. So it's no surprise that we can see in the visible light spectrum because that's what the sun puts out, mostly. Visible light, ultraviolet, UV. What do you guys know about UV? Is it good, bad?
It could be good and bad.
Ooh, good and bad. What's the example where it could be good?
It's good for your bones. The light.
Yeah.
Yeah.
Okay. No, in a little bit, small amounts.
And burning.
What do you think back there?
Isn't it bad because like your eye?
So it,
Oh no, you can't UV. Oh no, that's like sun rays, right?
yeah, but the sun's visible, right?
Yeah.
But there's stuff coming from the sun that you cannot see, right?
Oh, and then that's like doesn't that like cause like skin cancer if it's like a high?
Absolutely. Ultraviolet, right?
Yeah.
There's UVA, B, and C. It's UVB that's the bad stuff. Okay. That's when you wear sunscreen, right? You're protecting from UVB, right? So ultraviolet light. So by the way, do you have sensory for ultraviolet? Can you feel ultraviolet? No, right? But you do have a detector for it in your body, right? You go to the beach, right? And you hang out at the beach for a couple hours. You come home. You didn't notice it while you were at the beach, but you come home and all of a sudden you look in the mirror and you are red, right? So you have a delayed detector, right? Your skin turns red when you're exposed to enough of it, okay? You can feel infrared, that's heat. You know, put your hand up near a hot oven, right? That's infrared, okay? Microwaves, well, you know about microwaves, right? You heat up your food sometimes in your microwave oven, right? That bounces around tiny little electromagnetic waves called microwaves around your oven, around your microwave oven. Radio and TV. Radio waves are how Wi-Fi and Bluetooth work. Okay. TV similarly. Okay. These are all forms of electromagnetic radiation, and including X-rays. Okay. You can see certain kinds of electromagnetic waves, like visible light. You can feel others, like infrared, and then you have no sensory receptors for certain kinds, like ultraviolet and X-ray, or radio for that matter. Okay, can't see, taste, touch, or feel them. Okay, but they are there. We can measure them. Okay, good. So we have our three categories, right? Waves in a medium, particles, and then waves as well. So why don't we include electromagnetic in this number one here? Well, there's a good response to that. Number one is waves traveling through some medium. The medium is air or water or something like that. Electromagnetic waves, visible light, you go outside at night and you look up at the sky and you see the stars, right? Well, between the stars and us, so the nearest star, excluding our sun, the nearest star to us is about 4 light years away, okay? So really long ways away. Traveling at the speed of light, it would take you 4 years to get to the nearest star, okay? Speed of light is 187,000 miles per second, so you'd have to travel quite fast for quite a long time to get to the nearest star, right? It takes light 8 minutes and 36 seconds to get from the sun to you here on Earth, okay? So light travels fast, but these things are far away, okay? So if waves typically travel through a medium, but the sun and other stars are getting light through the vacuum of space to us, then that means these waves, these electromagnetic waves, must be able to travel through space with no medium in between, with nothing in between us. Okay, so that's the special thing about electromagnetic waves. That's why they're not in category one. Electromagnetic waves do not require a medium. We describe them as being what we call self-propagating waves. They are their own medium. Okay, electromagnetic waves, visible light, radio, and all these others are electric and magnetic waves that travel through the vacuum of space from other stars to us, and they can travel through, anything. Right? They travel on their own without anything in between. Now, of course, they can go through the air in the room and all that good stuff, but they don't require a medium to travel through. They're self-propagating. That means nothing to you right now. Just let it sit for a while. Hang on to it. Eventually, you'll go, oh, that's kind of a neat idea, or not. All right, let's get a couple definitions out so we're clear on what we're talking about over the next few slides. For elements and atoms, we have some things we've got to be able to, a couple ways we've got to be able to discuss them, right? So we're going to talk about transmutation in a moment here and changing of these certain numbers. So we've got a couple important numbers. Every element, so every atom, has, starting off, 2 important numbers that you need to know about it, okay? One is the atomic number, given as a capital Z. This is the number of protons the atom has. So let me just briefly draw a terrible picture. Okay, so what I've attempted to draw is a single atom of carbon. Carbon's number 6 on the periodic table. If you look at the periodic table and find the one with the 6 at the top left, capital C, top left. If I can help out at all. Periodic table? Okay, good. So I just drew carbon the best I could, okay? So atoms have have this structure, okay? We discovered this structure in like 1904, 1905. Anyways, we've known about the structure of atoms for quite a long time, okay? We just kind of take it for granted now. Like if you think about an atom in your head, you probably were thinking about something close to this appearance, okay? Maybe not exactly, but something close to this appearance. Atoms are described as having a dense nucleus. This is where all the weight or mass of the atom is, all the heaviness of the atom. In the nucleus of an atom, you're going to have positively charged protons. The plus sign is a thing called a proton. If I draw anything with an N, that's a thing called a neutron. If I draw something with a minus sign, that's an electron. Okay. So atoms have in their nucleus protons and neutrons. Okay? I've only drawn the protons right now. So these three different particles that atoms are made of, protons, neutrons, electrons, these signs, plus, minus, and neutral, indicate the electric charge. Okay? So a proton has a positive electric charge, a neutron has no electric charge, and an electron has negative electric charge. You probably are semi-familiar with electric charge because you have a charged car battery, right? And you charge your phone every day. Okay? That's what I mean by electric charge. You might not be familiar with what negative and positive mean, but you probably have held a AA battery before, right? It has a negative end and a positive end, right? It's negative electric charge, positive electric charge. Okay? All the way down to the level of atoms, there are negative electric charges and positive charges. Okay? Don't worry about what the difference between them is, just negative is the opposite of positive. Okay? There's some technicalities about what and why, but we're not going to worry about that. Atoms have a dense nucleus. That's where all the protons live. Protons are the biggest, heaviest part of the atom. They live in the nucleus. So do the neutrons, if I'm going to draw any, they'll be in the nucleus right here in the center. Orbiting around the nucleus in what we call shells, shell levels, are electrons. Okay? Now, don't worry right now about why I only drew 2 in this first one and there's 4 out here. What you should pay attention to is, if you count the total number, 1, 2, I drew the wrong number. What a dummy. Hang on. Pause. Negative, negative. Put the other negatives over here. These numbers were supposed to match, and I just totally flipped it up. Okay, what you should pay attention to is the total number, okay? 1, 2, 3, 4, 5, 6, okay? 6 total electrons orbiting around this dense nucleus, okay? How many protons, how many positives do you count? 6, okay? These two numbers in a happy neutral atom are going to be equal, okay? All atoms try to make these numbers equal, okay? All atoms have a dense nucleus. This number in the nucleus on normal atoms doesn't change, okay? And they will hold on to, or have in orbit around them, the same number of electrons that we have in protons in the nucleus, okay? The atomic number of an atom is the number of protons in the nucleus. The number of these little positively charged guys in the nucleus of the atoms, this tells us what the atom is. Okay, what element it is, in other words. Okay, 6 protons in the nucleus, we know it's carbon. Okay, go up to 7 protons in the nucleus, right? That's nitrogen. Okay, go up to 8 protons in the nucleus. So if you're looking on your periodic table, right? Just let me come up to the board. Looking at your periodic table, you have carbon in the top right. You see the number 6 protons in the nucleus. Go over one more in that same row, capital N nitrogen, 7 protons in the nucleus. Go over one more, 8 protons in the nucleus is oxygen. The atomic number shown here in the top right of each element tells you what element it is. Okay? The atomic number identifies the element. If that number, this is important, if that number changes, okay, which does happen in radioactive elements, if that number changes to a different number, it's a new thing now. It's a different element. Okay? For example, uranium here has 92, capital U, you see that down on your guys' right, uranium, 92, it's an atomic number is 92. It has 92 protons in its nucleus. Uranium's radioactive. Okay? So when uranium undergoes a radioactive decay event, which we will talk about, it can turn into thorium, which is 90. Okay? It does it again. Okay, 90. We come up here now. I know it gets a little confusing. 90 goes to 88, radium. Okay? 88 down to 86, radon. Earlier we said uranium decays into radon, right? So there's radon right here at 86 there. Okay? Decay again, and you get polonium. Decay again, and you get lead. And it happens that uranium stops decaying when it gets to lead. Lead is the heaviest stable element. Don't ask me why we went two at a time. It's harder to explain why those ones are in between the two. But two at a time, going by two at a time, uranium can decay into lead. Okay, and on its way to lead, it becomes radon. Okay, changing the number of protons in the nucleus changes the element. Okay, that's referred to as transmutation, which I'll describe more on the next slide. Top right on the periodic table of each element tells you the number. That's the atomic number. That's how many protons are there. That's identifying the element, in other words. There will be another number on our chart. It's at the bottom of each element. So notice at the bottom of each element there's another number, right? So what do you see? So for carbon, it has 6, right? So it happens to be in the top left on our chart, but it says 6, yeah? What's the number down underneath the C? 12.0111, right? It's a number a little bigger than 12, okay? This is telling you the atomic mass, okay? The atomic mass is adding up all of the protons in the nucleus plus all of the neutrons in the nucleus, giving you the total mass of the nucleus, the center of the atom, which is where all the heavy stuff is. Electrons, for all intents and purposes, don't weigh anything. Okay? So if we want to know how big or how heavy an atom is, you want to know its atomic mass. If you want to know what the atom is, you need to know its atomic number. So that's why there's two numbers. Okay? So take, let me erase some of this junk here. Too much stuff up on the board. All right, so take the atomic number and subtract from it, atomic mass, and subtract from it the atomic number, right? So for carbon, what was the mass number?
6.
No, no, no.
Oh,
12. 12.0111, right? So subtract from it the atomic number, which is the 6, okay? And you get 6.0111, right? This is how many neutrons, you'll find on average in the nucleus of a carbon atom. So it's a number, it's not exactly 6, but it's roughly speaking 6, right? If you were to round down, which is what you would do in this case, it'd be 6. So on top of having 6 protons, an atom of carbon will also, on average, be found with 6 neutrons in its nucleus, giving the nucleus a total mass of 12. Okay? For reasons I won't go into, it's not going to be exactly 12, but it's roughly speaking 12. That's what you call the neutron number. So, if you want to know how big an atom is, how heavy it is, that's the atomic mass. It's the mass of the atom, okay? If you want to know what the atom is, you want to know its atomic number, capital Z, okay? That's given at the top of the element. If you want to know the neutron number, take the total mass and subtract the atomic number from it. That'll tell you how many neutrons the atom has. Okay. You guys okay with those three different numbers? Okay. So we have atomic number telling us what it is, atomic mass telling us how heavy it is, and neutron numbers useful. All of the chemical properties, all the way the atom's going to behave is going to be given by the atomic number. Okay?
Okay, so will you say those three
Yes,
one more time?
yes. So what I just said?
You said it, yeah, atomic mass.
So there's atomic mass,
Uh,
how heavy it is.
Okay, so
Okay.
atomic mass equals heaviness.
Mm-hmm. Atomic number identifies the element, tells us what it is. Like we know every time the atomic number is 6, it's carbon.
Yeah.
Every time it's 7, it's nitrogen. Every time it's 92, it's uranium, right? So atomic number tells us what it is, and neutron number just tells us how many neutrons it has, okay? For most purposes, we don't care how many neutrons it has, okay? The neutron number will help us identify something called the isotope later on, but right now, we care mostly about what the element is, atomic number, and how big it is, atomic mass. Okay. All of the chemical properties, all of the way the atom will behave with other atoms is going to be dictated by how many protons are in this nucleus here, okay? You take one of these away, you take an electron away. It's going to change the chemical behavior of that atom, okay? Oxygen will bond with hydrogen because of its total atomic number, because of its atomic number. Oxygen has 8, hydrogen has 1, and because of that and the rules of chemistry, those two things are going to bond together, okay? If those numbers were different, they would not form a bond, okay? The way atoms behave chemically with each other is determined by the atomic number, okay? How many protons we have here tells us how many electrons the atom's going to hold on to, and these electrons are what interact with the nearby atoms. So atoms interact by either sharing, giving, gaining, or sharing electrons between each other. And the number of electrons is given by the number of protons. Okay. We don't need that very much right now. I think the only thing I really need you to have right now, because we have a whole physics module to go through in months from now, all thing I need you to get right now is the atomic number, number of protons. Atomic mass is the heaviness, the total weight of the atom. Okay. Radioactivity is the spontaneous emission of particles or photons from the nucleus of an atom. Particles you have already. Okay, we described what those are. They're little pieces of the atom, protons, neutrons, or electrons. You may not know what a photon is yet. Okay, so remember we said there's 3 categories of radiation, right? There's waves in a medium. We don't care about that for right now, sound waves and water waves. There's particle radiation, particulate stuff, protons, neutrons, electrons. Then there was electromagnetic radiation, right? Visible light, radio waves, infrared, ultraviolet, X-ray, all that stuff. Well, those waves, like the waves of radiation, visible light coming from the light in this room here, okay? If you take and start to break the waves apart, eventually you'll get down to individual little pieces of the wave, okay? Those little pieces are called photons, okay? So they're pieces of light, okay? Now, so a photon is an individual particle of light, in other words, okay? Can't hold a photon like you could with a proton or neutron or electron, but it's a piece of light, okay? It travels at the speed of light, but it's a piece of light. That's what a photon is. So radioactivity is just the spontaneous, in other words, random emission of particles or photons from atoms. I'm losing my voice, sorry guys. All atoms do not decay. All atoms do not undergo radioactive decay. Only some do, okay? Carbon and nitrogen and oxygen and all these smaller elements do not undergo radioactive decay. In other words, they're not radioactive. Once you get to big enough atoms, the ones we're going to talk about, those become radioactive. Uranium and polonium and radium and those things, these heavy, heavy elements. Once you start to cram more and more and more particles into the nucleus of an atom, the more and more unstable it becomes. Okay, it starts to jiggle apart, okay, break apart. So a decay event is just an atomic nucleus with excess energy emitting a piece of itself, a single particle. Alpha, beta, or gamma emissions. The reason why it does this is to become more stable. Okay? All atoms, even the unstable ones, would like to be stable. Okay? And to gain stability, they have to shake off excess energy. And the way they shake off excess energy is by firing away pieces of themselves. Okay? By losing pieces. Okay? So some atoms, which are big enough, are unstable, and to regain stability, they shake off pieces of themselves. Okay? That's radioactivity. Every time it does that, that's a decay event. Okay?
And that happens every single time?
Yeah, every time there's a radioactive decay event, that's a piece of the atom breaking off and shooting away.
And that only happens in electric
That only happens in very big atoms.
or very big?
Yeah, very large atoms. Like, again, hydrogen and helium and carbon and all the general stuff that we're made of doesn't do that. Okay? But certain types of bigger ones like polonium and lead and potassium, right? Special kinds of potassium, they're big enough to be unstable.
So like metals?
Yeah, yeah. The metals is a tricky one because almost everything on the periodic table is a metal. That's a tricky one. But you're on the right track, I think. Yeah. Okay, so let's talk about these different types of decay events that can happen. Remember, there's three. We called them alpha, beta, and gamma. You need to remember atomic number and atomic mass to make this make sense. Okay, so take an atom. It's happy. It's sitting there minding its own business, but it's too big and it's unstable. Okay, if the decay that it undergoes is an alpha decay. An alpha decay will be the emission from the atom of 2 protons and 2 neutrons out of the nucleus. So here's the nucleus of a big atom. When that atom loses, or if that atom loses, a particle made of 2 protons, 2 neutrons, we call that an alpha emission, an alpha decay. Because we've lost 2 protons, our atomic number goes down by 2. That's why when I was doing that over there with uranium, I was going down by 2. Okay? Because we lose 2 protons, we lose 2 positive charges from the nucleus. Now that thing's going to change. It's going to go down by 2 on the periodic table. Okay? Whatever its atomic number was, it's going to decrease by 2 because 2 pieces that are positively charged have left the nucleus. So the Z number, atomic number, goes down by 2. But if you count the total number of pieces that left that atom, there's 4 pieces that left, right? 2 protons and 2 neutrons. So that it lost a mass of 4. Okay? What's most important here for the element is that because we lost 2 protons, we've now changed into a new element. So wherever we were at, whatever our atomic number was, we're now down 2 on the periodic table. So like, again, if we were uranium at 92, we go to thorium at 90. If it's a little atom of uranium, pops off a little piece of itself at alpha emission, loses 2 protons, it's now thorium. It's a different thing now. You know, you lose a piece of yourself, you lose an arm or a leg, you're still you, right? Atoms don't work like that, okay? If atoms lose pieces of themselves, right, they're different now. They're a different thing now, okay? Uranium goes to thorium, for example. Okay, that's one that I think is easy, right? Alpha emission, 4 pieces, 4 little particles come out. Two of them are protons, so we go down 2 on the atomic number, and our mass goes down by 4. The mass is less important than the atomic number. And importantly, we're a different element now. We're a new thing, okay? This is referred to as transmutation. When there's a decay event, the atom transmutates. It changes. Mutation is like a change, right? It changes into a different thing. Now here's the one that's a little funky, okay? Beta. Beta emissions are a little funny, so allow me to attempt to describe this, okay? So in the nucleus of the atoms, we had two things, right? We had protons, positive electric charge, and we had neutrons, no electric charge, okay? Secretly, not so secretly, a neutron is really a combined proton and electron, okay? If you take a proton of +1, right, and you add to it an electron of -1, what do you get? +1 -1? 0, right? A neutron is really a proton and an electron combined together, okay? So, if a neutron in an atom breaks apart, okay, because really, again, what a neutron really is a proton and an electron combined. A neutron, these little things that I was drawing with an N, are really just a plus and a minus together, okay? All right, so in beta decay, a neutron, which is really a plus and a minus together, okay, breaks apart. The minus will go away. The negatively charged electron will be shot away from the atom, and the proton will stick behind, okay? So a neutron here, where the red laser pointer is, minding its own business, decays. This is random, these happen randomly, but a neutron decays. It will turn into a proton and electron pair, okay? Because of physics, the electron is shot away from the atom, and the proton stays behind, okay? This is called a beta emission. A beta emission or beta decay is the emission of a negatively charged electron from the nucleus of an atom. When a neutron converts or decays into proton-electron pair, electron is shot away. Here's the thing. That neutron was neutrally charged, but then it turned into a positively charged proton. So we added a positive charge to the nucleus, meaning we're going to go up on the periodic table. Wherever we were, we go up by 1. So if we are uranium, I can remember what the one uranium is. Go over here. The name's actually written down, right? So if we're uranium at 92, and uranium, instead of having an alpha decay, happens to have a beta decay event, which can happen, uranium turns into neptunium, okay? Goes up 1 to 93, okay? Importantly, if you look at the A for atomic mass, the mass is unchanged, right? All we lost is a little tiny electron, and those don't hardly weigh anything, okay? So the mass is unchanged, and we went up 1 on the periodic table, okay? It is more stable for an atom to have a proton than a neutron, okay? So that neutron can transmutate into a proton-electron pair. Electron goes away, proton stays behind, making the atom +1 on the periodic table, turning it into whatever 1 up from wherever it was is. All right, so wherever it was, it goes 1 up.
So beta is +1,
Yeah, beta is turning a neutron into a proton.
and then alpha is
-2.
-7.
Alpha emissions are, if you ignore like what's happening physically to the atom, just pay attention to the numbers. Alpha emissions are -2. Beta emissions are +1 to the atomic number. Alpha emissions are much more harmful than beta emissions. It's like getting hit with a pellet gun versus like a tank round, right? You'd rather get hit with a pellet gun, right? Tank rounds are going to be a lot more harm, right? And it's due to physical size, right? These alpha particles are big. An alpha particle, by the way, secretly, how many protons is this? No, the alpha particle here. 2, right? What's 2 on the periodic table? Top right. Helium. An alpha particle is really a helium nucleus, okay? It's big, okay? Alpha particles are big, beta particles are small. It's size that matters here, okay? What matters for kinetic energy? If you've been with me for long enough, I've lost my most seniorist students, but the ones who've been with me for long enough, remember the formula for kinetic energy. Kinetic energy is 1/2 mass times velocity. So two things that count for kinetic energy, mass times velocity squared, excuse me. Two things that count for kinetic energy, mass and velocity, okay? Assuming a beta particle and an alpha particle were traveling at the same speed, the alpha particle is going to have more energy because it's bigger, okay? It's like a semi-truck hitting a wall versus a smart car hitting a wall, okay? The semi-truck will do more damage if they're both traveling at the same speed. Semi-truck's going to do more damage. Why? Because it's bigger, right? And to use it in terms that we like, because it has more mass, right? Okay, good. So alpha particle, big, beta particle, small. Alpha particles are more harmful. Okay, these are the two types of particulate radiation. These are the two, because there's only three things to remember, three types of decay events to remember. Alpha particle is the big one, beta particle is the small one. Alpha particle goes down by 2, beta particle makes the atom go up by 1. The last one, because there's 3, is gamma. Gamma emission's special. Gamma emission is the emission of a gamma photon, a piece of light more energetic than an X-ray. Gamma rays are what made the Incredible Hulk, if you are into comics at all. Gamma rays. All right. He would have just died, by the way. But it's a comic book. Okay, so gamma rays. Here's the interesting thing about gamma rays. A gamma ray is just a photon, a particle of light. And what you need to know about photons is, photons have no electric charge. So they are neutral, no electric charge. Photons have no mass. They're not a thing that you can hold and weigh, okay? So, if there's no electric charge leaving the atom and no mass leaving the atom, does the atomic number change? No. Does the mass change? No, right? Gamma emissions are special because they leave the atom unchanged, except for the atom has lower energy than it did before. Once the emission happens, gamma particle leaves the atom is unchanged except for its total energy. The energy goes down, because the photons do carry energy. So they are massless, chargeless, but they carry energy, okay?
So if they leave the atom,
So the way,
and change it.
unchanged in mass and unchanged in charge. The other way to say this is, only excess energy is emitted. An atom shakes off some excess energy by emitting a gamma ray. The degree of biologic harm caused by each type of radiation depends on its mass and charge. So, alpha particles are harmful. 1, because they're big. 2, because they're electrically charged. Beta particles are less harmful because they're smaller, but they're still electrically charged. Gamma rays have no mass, no electric charge. However, they're still harmful, but much less so than alpha or beta particles, gamma rays.
Don't have an electric charge.
Gamma rays have no electric charge, no mass. Gamma rays are, for all intents and purposes, the same thing as X-rays. In fact, this might be more than you want to hear, so plug your ears if you want. The only difference between gamma rays and X-rays is their origin, where they come from. Okay? Gamma rays come from the nucleus of an atom. X-rays come from the orbiting electrons. If you've been with me long enough, you've heard of us talk about X-ray production. Okay? X-rays come from electrons. Gamma rays come from the nucleus of an atom. That's the difference between them. It's the difference in their source. Good. Okay, so we want to know, like, what do you mean biologic harm, right? So harmful to living things, but not like harmful to my tabletop here or my computer, okay? So we want to know, like, how, because, you know, the table's made of atoms, so is my book. I'm made of atoms. So why does radiation, why does radioactivity, why is it harmful to me and you, but not my table or my pen or my cup of coffee, right? What's the difference, yeah? So we're all made of atoms. The problem is that our atoms that constitute us have to continually produce new stuff, right? Our DNA has to continually produce new stuff, new pieces, right? We're constantly breaking down and rebuilding, right? That's how our bodies work, right? On average, the lifespan of a single cell in your body is 24 hours, okay? You have cells that live your entire life, like your neurons, and you have cells that turn over daily, like intestinal cells, okay? But on average, 24 hours is the time frame for a cell. It's the activity part of it, it's the living part of it that makes it harmful, okay? If the radioactive event, decay event happens to the table, it's gonna harm some of the atoms in the table. But the reason why we don't see the evidence of that is because the table doesn't have to continually maintain itself. The table is just kind of a stable configuration, right? But you have to continually break down and rebuild, okay? And radioactive particles can change the structure of atoms such that when your body is breaking down and rebuilding, it might rebuild it wrong, okay? That's where we get cancer from. Incorrect rebuilding instructions, right? Okay, so here's what these radioactive particles can do. They can do something called ionizing atoms. Radioactive particles can harm other atoms. So there was an atom over here, it was radioactive, and it fired off an alpha particle, okay? And over here was a living thing minding its own business, okay? If that alpha particle happens to hit that living thing minding its own business, it can interact with the atoms of that living thing, okay? And it can rip out the electrons in orbit around that atom. And here's the problem. The electrons in orbit around the living thing's atoms are what give the chemicals their shape in that living thing. So if you take away an electron, whatever bond that atom was having with a nearby atom might break, okay? H2O is the most common molecule in your body, okay? H2O, hydrogen and oxygen, right? If the bonds between them get broken by some radioactive decay, H2O can turn into H2O2. You guys know what H2O2 is? You should. You probably heard of hydrogen peroxide, right? Hydrogen per oxygen. There's one hydrogen for every oxygen atom, right? H2O2, right? What's hydrogen peroxide good for? Yeah, you put it in a cut so you don't get what? Infected, right? So what's the infection caused by the way? Bacteria. So it can kill bacteria. Bacteria are living things, yeah? And you're a living thing, right? That's why you don't like drink hydrogen peroxide, right? So that's why you don't inject it into your veins, right? But these radioactive particles can turn your water into hydrogen peroxide, okay? Not good, right? Bad for living things that can damage your cells, okay? If this atom here that's having an electron ripped away from it is part of your DNA strand, okay? Well, that might break your DNA strand, all right? Now, 9 out of those 10 breaks are going to be repaired by the body, but that 10th one's not, okay? And there's a cumulative effect here, okay? Similarly, beta particles can do it too. Now, let me backtrack here for 1 second. Alpha particles do it by pulling. They pull the electron away from the atom, okay? Opposites attract. A positive charge attracts a negative charge. However, like charges repel. So a beta particle zooming into an atom will push out an electron orbiting around an atom, okay? Doing the same thing, right? Notice this atom has lost an electron, and so has this one. It's just exactly how it did it will change, okay? Gamma radiation can do this too. Gamma radiation can ionize, remove an electron from an atom. So that term ionization, I believe I'm going to bring it up here in a little bit. Yeah, we'll get there. But just to give it to you, ionization is the creation of a charged atom from a neutral one. You had a neutral happy atom, you pulled an electron away from it, it now has an overall charge, okay? It had the same number of positive and negative charges, this happy atom in your body, and you removed an electron from it. Now it has more positive charges than negative. It has been ionized. Ionization is the reason why certain types of radiations are harmful, okay? Sound waves are not harmful to your living cells because sound waves don't ionize your living cells. X-rays are harmful. X-rays can ionize your living cells. Gamma rays can ionize. Beta and alpha particles can ionize, okay? Visible light cannot ionize living cells, cannot ionize anything, living tissue, okay? Radio waves and certain types of ultraviolet can't do it either, okay? Some types of ultraviolet can, like UVB, okay? Ionization is the problem. This is why certain types of radiation, again, are harmful. All right, natural radioactivity. Natural radioactivity, again, one more time, there's 3 types of it: alpha, beta, and gamma, okay? Now here's the problem. Because alpha and beta particles are electrically charged, they are not penetrating to the body, okay? That sounds like it might be a good thing, not penetrating, right? But in fact, if you're going to be hit by radiation, you would like it to pass through you, okay? If it passes through you, that means it didn't dump all of its energy into you, okay? So the less penetrating a form of radiation is, the more harmful it is. The less penetrating a form of radiation is, the more harmful it is. Alpha rays are so harmful, alpha particles are so harmful because they penetrate less than 1 millimeter into body tissues. In other words, they dump all of their energy into the first thing they come in contact with. Their energy is therefore more concentrated in those body tissues and thus more harmful. Alpha particles emitted into the lungs by smoking concentrate into that area and then begin to emit radioactivity, alpha, beta, gamma, in all directions. And so all of the radiation from those inhaled particles stay right in the lungs. This is why smoking causes lung cancer and not, like, kidney cancer, right? Because it's happening in the lungs.
Are all 3 of those, alpha, beta, and
Gamma?
gamma, are all those 3, I forgot what I'm going to say, like they're all 3 together all the time?
So, good. So any of the 3 can be happening at any given time. Okay, so it can be just alpha, just beta, just gamma, any combination of them. They're all versions of this of radioactivity, though. Yeah. So you're not going to be able to tell. Like when I turn on a Geiger counter, I can't tell if it's alpha or beta, right? But I will be able to tell that there's some decay event that's happened. Yeah. It's a good question. Yeah. So any version of that, right? Typically, what will happen is, like, after an alpha or beta emission, you'll have a gamma emission following it, but there's no, like, set in stone way that this happens. And you don't need to, if there were, you wouldn't need to worry about that. Yeah, that's a good question, though. Okay, so penetration. The penetration ability of some form of radiation is inversely related to biologic harm. Inverse relationship. As one thing goes up, the other goes down, okay? If the radiation is more penetrating, it is less biologically harmful. If it is less penetrating, it's more biologically harmful. Inverse relationship. All right, so alpha is going to be the worst. Let's look at our table here so we can get a feel for this. Alpha, less than 1 millimeter, big harm. 2 up arrows for harm. Beta emission, less than 2 centimeters. Still 2 up arrows, so still harmful. Gamma rays, more penetrating than X-rays. Okay, so the harm is less, right? More highly penetrating equals less biologic harm. And X-rays are similar. They're on par with gamma radiation. X-rays penetrate the body. By the way, if X-rays didn't penetrate the body, you guys wouldn't be taking an X-ray program because we wouldn't be able to make images, right? If they stayed in the body, didn't get to the image receptor, there'd be no images to take.
And alpha and beta stay in, they penetrate as soon as they touch something.
Yeah, as soon as they hit the first tissue they hit, they're going to stay there.
So then that's why they're dangerous.
Yes. Yeah, if an alpha, beta, and gamma particle, if all 3 had the same energy, yeah.
When are you going to break?
Oh, I'm going to oh my gosh, I should be stopping like right now.
I need to see Kylie with you guys.
Okay, cool. Got it? Cool. Okay. I'm glad she said something because I need to stop soon. All right. I don't know how far we're going to get through this, but we're going to do our best. Okay. So if an alpha particle, a beta particle, and a gamma ray, all 3 had the same energy, okay, the alpha particle would do more harm than the beta particle. The beta particle would do more harm than the gamma particle, okay? Even if they all have the same energy, the alpha particle does the most harm because it stops the quickest, okay? It dumps all of its energy right into the tissue, whereas the gamma ray continues through the body and doesn't have to interact with the body. Lastly, I want you to pay attention to the source. Alpha, beta, and gamma all come from the nucleus of atoms. X-rays do not come from the nucleus. X-rays come from the orbiting electrons around an atom. And very lastly on this, the mass. Mass is important. This is one of a couple of reasons why alpha particles are harmful. Alpha particles are about 8,000 times heavier than a single electron. We measure atomic mass in some cases relative to electrons, and electrons. So electrons being the thing, a beta particle is an electron. It's got a mass of 1 in these units. An alpha particle is 8,000 times heavier than that. Okay, so it's so much bigger, and it carries a bigger electric charge. It's less penetrating, and therefore more harmful. Okay. I'm going to do isotopes and half-lives next time at the very beginning of class, because I'm going to go ahead and stop things now. So we didn't make it all the way through, but we'd actually